I'm Jane. I'm here to present the last project of my PhD study. We built a search engine that reads data as needed from SSDs. SSDs are fast, especially the NVMe SSDs. The SSD on the top, in particular, has sequential read performance of 3.5 gigabytes per second. It can do random read with half a million IOPS, and it's very cheap. And to prove it's very cheap, I'm going to just buy one right now. One click. Now let's move on. It's so fast, many application systems have been optimized for SSDs, right? For example, key value storage, graph storage, file systems, and many more. But search engines are overlooked. So search engines are very important and very widely used. Elasticsearch, for example, is the most popular search engine in the market. It's ranked 7th among all the databases in the world. The rank is higher than well-known search databases like Redis and SQLite. It is widely used. It's used by Wikipedia to search the articles. It's used by GitHub to search your code. And it's used by Uber to generate a dynamic price for your ride. So you probably has been using it today. And there are more user cases for Elasticsearch and search engines in general. Search engines are pretty challenging for storage systems because first they demand low data latency because users are waiting for the results of the queries. Another reason is that search engine demand for high data throughput because search engine retrieve information from a very large amount of data. And another reason that's challenging is because it demands high scalability because data grows over time. So can we solve the problem by just using more RAM? RAM is very critical in existing search engines. As Elasticsearch user puts it, your RAM will limit all the other resources. I guess it's okay to use more RAM at a small scale because the total cost is low, but it's cost prohibitive at large scale. Because the data goes fast, and it's kind of a waste to have a large RAM because you rarely read and process 100 gigabytes per second in a single node. So if it's not a very good idea to use a lot of RAM at a large scale, the question is, can search engines perform well with a small memory and a fast SSD? By small memory, we mean that the RAM is much smaller than a working set. Our answer to this is yes. We have built a search engine that performs well on small memories. And for some workload, it could outperform other engines with entire data set in the memory. For some workloads, it cannot. But we do see the potential for it to improve the performance significantly. The philosophy behind this search engine is that we read data as needed. By that I mean we use small memory. We read data from SSD as needed. We do not attempt to cache the data in the memory. Instead, we attempt to read the data from SSDs efficiently. There are some intuitive reasons why this might work. First is SSD have very high read bandwidth and IOPS. The SSD I mentioned before can read the entire drive in 5 minutes. And the higher bandwidth is possible with a RAID. There's another reason. Like other components of the system is more likely to be the bottleneck, like computation network. So to optimize such a read-as-needed system, we must do the following things. First, we must reduce the read amplification because the SSD bandwidth is still limited. We need to hide the I/O latency because SSD latency is still lower than the RAM. We need to use large requests to improve the device efficiency because SSDs like large requests. In this work, we apply 4 techniques to build this read-as-needed search engine. We're going to introduce them in more detail later. But here is a gist. First, we group data by term. where we try to reduce read amplification and use larger requests. The second technique is two-way cross-aware Bloom filters, where we try to reduce the read amplification. And the third one is adaptive prefetching, where we try to hide the I/O latency. And lastly, we trade disk space for I/O. We trying to reduce the read amplification. We believe our work has the following contributions. First, we propose 4 techniques to improve the search engine performance with small memory, large data set, and a fast SSD. We have built an open source search engine from scratch. It has 11,000 lines of C++ code. And we find that it's very hard to find a benchmark to benchmark search engines. So we built a benchmark for evaluating search engines. It's based on Wikipedia. It has a variety of queries to suggest the system. And lastly, we built a search engine that performs better than the state-of-the-art search engine, Elasticsearch. It can increase the query throughput by up to 2.7 times and reduce the latency by up to 16 times. So this is the outline of this talk. We just covered the overview. Now let's get into the techniques. These are the techniques. They're designed, are guided by the Wikipedia data set. So we're gonna use the examples from Wikipedia a lot. Now let's introduce the first technique. Before introducing the first technique, let's introduce some background. In the search engine, the documents are stored in a document store, and you can easily find the document by its document ID. And let's say if you want to search Tuckman, which is the last name of some martial artist, and you're going to use the index to find a list of document ID, and this document contains the term Tuckman. And then you're going to need some term frequency to rank the document. Term frequency indicate how many times a term appears in a document. And if you are doing phrase query, you're going to need term positions. In this example, Tuckman is the second word in the document, so the term position is simply 2. And lastly, you're going to need some byte offset of the term, so you can quickly locate the term in the document and highlight the term in the document and generate a snippet to show to the user. So data in Elasticsearch is grouped by stage. By that I mean, like in this example, the data of Tuckman is stored in 3 different files. Data of the same stage stay in the same file. So you have data for scoring in one file, you have data for phrase match in another file, and then you have some data for highlighting stage in another file. Now let's see how much I/O is needed for Tuckman. Let's put a counter there, and if you want to process this query, you're gonna need some. You're gonna need the term frequency and document ID, and then you're gonna need some. You probably need some positions, and then you need some offsets. Now we can see the I/O count is 3. But the problem is that the transfer data is often wasted. For example, the data for Tuckman is only about 30 bytes. But we did 3 I/O, which has a size of 12 kilobytes. And in that process, we actually read a lot of data of the nearby terms. But in fact, the data of Tuckman can fit in 4 kilobytes, which is one file system block. And actually, small terms like Tuckman is very common in Wikipedia and in general in many data sets. One more click. Let's go back. What? So because due to that observation, WiSER actually groups data by term. This is what we mean. We place the data of the same of the same tense term to the same place in the same file. And as you can see here, all the data for Tugman is in one place. Now let's see how much I/O do we need for Tugman. So let's put another counter there, and you can see that we can get all the data for Tugman in one I/O. In that case, we actually can reduce the I/O by up to 3 times. Now let's introduce the second technique, which is two-way cross-wire Bloom filters. Let's also again start by introducing some background. Phrase queries offer very high accuracy in search engines. For example, if you search United and the States, both of these documents will come up because both of them contain the term United and the term States. But if you want to learn about a country, you can search the phrase United States. If you search a phrase, only the document on the left will show up because it contains the phrase. Phrase queries offer very high accuracy, but they demand a lot more data. This is how phrase match works. Let's assume that you have this data, and by looking at position, you know that United is the second word in the document and States is the third word in the document. By that, you can see that United States are together in the document and they form a phrase. For the example on the right, United is the 4th word in the document and the States is the 6th in the document. By looking at that, we can see that there's one more word between these two terms, so they do not form a phrase. A term can appear many times in a document. Therefore, we can have many positions. And because of that, we have to process a lot of position data, and that's the reason that phrase query demands a lot more data. We try to reduce the traffic size by regular Bloom filters, and it does not work. It actually increases the read traffic. So we have to invent something, some special Bloom filter to do the job. And here it is. WiSER adds 2 Bloom filters to enable two-way filtering. Originally, we only have position in the index of the search engine. But for WiSER, we add a Bloom filter for all the terms after, for the term after each term. So for example, in this case, States is in the after filter of United, and the President is in the after filter of States. Now we also have another filter we call before filter, which has the term before, which contain the term before each term. By having these 2 Bloom filters, we can check if United States is a phrase in the document by either checking if States is after United, or checking if United is before States. But wait, why do we add 2 filters? I mean, we can just do the job with 1. Having 2 filters will allow us to dynamically change the smaller filter for filtering. Hence the name two-way in the name of the technique. For example, let's assume that we have the filter size and the position size like this. If we check if States is after United, you're going to have to read 600 kilobytes of data, which is the filter in red there. But the problem is that the filter size is larger than the position size, which is the size, which is data that we are trying to avoid reading. So this is not good. A key observation here is that the 2 terms and the phrase query, they usually have very different popularity, which means they have very different filter size. So by observing that, we can just use a smaller filter to do the filtering and save a lot of I/O. For example here, we can just check if United is before States. In that case, we only need to read 60 kilobytes of data, in which case we can save a lot of I/O. WiSER only uses filter when it can reduce I/O, hence the crosswire in the name of the technique. Let's assume we have filter size and position size like this. In this case, if we check if states is after united, we're going to need to read a very large filter, which is not worth it. If we check if united is before states, we still have to read a lot of data, which is not worth it. So in this case, we just fall back to use the position to do the phrase match in this case. Now let's introduce the adaptive prefetching. Elasticsearch relies on the OS to do the prefetching. But the problem is that the operating system does not have any information about the query. So the operating system will just blindly prefetch a fixed size for all the queries. In contrast to that, WiSER adaptively prefetch the frequent used data to hide the I/O latency. We put the prefetch size along with the index. So if you search a more popular term like cheese, we're going to prefetch more data. And if you search a less popular term like tagman, we're going to prefetch less data. In this way, we avoid reading a lot of data. Last technique is shared disk space for I/O. WiSER compresses documents individually to reduce the replication. In Elasticsearch, multiple documents are put into this 16 kilobyte buffer to be compressed. This is to reduce the size of the compressed data. But the problem with this is that if you want to read document 3, you have to read all the documents before it. So in this way, you can decompress the data for document 3. In WiSER, instead, we compress the document individually like this. The catch here is that each of the documents will be slightly larger than Elasticsearch, but that's the trade-off we're making. So by doing this, if we want document 3, we can just read document 3 without reading all the previous documents. Now we have introduced other techniques. Let's get into the evaluation. We built this benchmark called WS Bench. It's based on Wikipedia, which has 6 million documents and 6 million terms. And it has a variety of queries. And we vary the term popularity in Wikipedia to suggest a system. Term popularity means how many documents or term appear. And we use a 16-core machine. We use SSD with peak read bandwidth of 2 GB per second and 200,000 IOPS. To evaluate how well each search engine can scale up to large working sets that do not fit in the main memory, we use a very small RAM size, which is a container size that runs the search engine, which is half a gigabyte. Now let's see how much read traffic can grouping by term reduce. In this plot, X is the term popularity. On the left side, there's less common terms. On the right is more common terms. And the y-axis is the normalized traffic. It's normalized because it's easier to see the difference. And because we normalize to the Elasticsearch size, so the size for Elasticsearch is always 1. And now let's look at the data for WiSER. So WiSER can reduce the read traffic by up to 3 times. We can see that the reduction of the traffic is more on the left side. That's because the less common terms waste more data. So there's more space for our improvement. Now let's see how much query throughput can grouping by term increase. This figure is the same as the one before, but just except that y-axis is the throughput. We can see that grouping by term can increase the query throughput by 2.6 times. The improvement of the throughput is highly correlated with the reduction of the traffic. So if you put this figure and the previous figure on the same page, you'll see they are highly correlated. Now let's look at how much read traffic can the two-way crossway Bloom filter reduce. We evaluate by fixing the term popularity of one term in the phrase and vary the popularity of another term in the phrase. And the x-axis shows the term popularity of the very term. On the left is slightly more like less common plus a common term, and on the right is more of a common plus common terms to form the phrase. And the y is the normalized I/O traffic. Again, we normalize to Elasticsearch. Elasticsearch data here is serves as a reference, and we have the data, or we have WiSER without the Broom filter, and we also have WiSER with a Broom filter. So by turning the Broom filter feature on and off, we can clearly show that the impact of this feature. So here we can see that the Broom filter can reduce the I/O traffic by 2.8 times. Now let's see how much query throughput can the filtering increase. This plot again is the same as the previous one, except that the y-axis is a throughput. We can see it can improve the throughput by 2.8 times. Again, the improvement of the query throughput is highly correlated with the reduction of the read traffic. Finally, let's look at how does small memory performance compare with larger memory performance. To evaluate this, we change the memory size from large to small, from left to right on the x-axis. And in this plot, y-axis is the read traffic. And we have two workloads here. On the top is the phrase query, on the bottom is the single term query. As you can see here, the read traffic goes up really quickly when we reduce the memory size. That's because when your memory cannot hold the working set size, you immediately start to read data as needed from the SSD. But WiSER in this case grows slower than Elasticsearch. Now let's look at the throughput of the engines. Ideally, we should have a flat line there for WiSER. In that case, that means the performance, the query throughput doesn't change as we reduce the memory size. That's ideal because if we can do that, we can replace memory with SSD without anybody noticing any difference. But the truth is the performance goes down. There are more space for improvement. That's this interesting case here where the small memory WiSER performance is higher than the large memory performance of Elasticsearch. That's for two reasons. First is because of techniques that we proposed. Another reason is that just because the more efficient implementation of the search engine in WiSER. And we also noticed that when the memory is very small, the system performance is bounded by the IOPS at the SSD. We believe that if we can replace it with a higher performance SSD with a lot more IOPS, we have the potential to reach the ideal performance there. There are more results in the paper. There are some final thoughts, actually questions for you. The first question is, does your application really need large cache or RAM? The second question is, will your application works just fine if it reads data as needed from fast SSDs? We asked ourselves this question, and we built a search engine that just reads data as needed from SSD, and it works just fine. And I should ask as needed. Thank you.
All right, thank you very much. Nice presentation. We have the time for a few more questions. So please come forward. There are 3 mics. One over there, and the other one, and the third one. So.
For the term query, how do you handle term query with more than 2 phrases? For example, like 3 or 4 phrases?
Oh yeah. The basic is the same. So it's the same for WiSER and Elasticsearch. But the tricky part is the technique 1, where we group data by term. It works also for other queries. How can I explain that? So the workflow of those multi-term query is the same in WiSER and as is in other popular search engines. But the technique one that we propose, which groups data by the term, will also improve the performance for those multi-term queries.
All right.
Hi, Bill Pulaski from Microsoft. Sorry about the light in your eyes. At the end, when you were showing your performance results, you made the point that some of the difference in performance is because it's a different implementation and you just did a better job, and some of it is because of the low memory techniques. And of course, that makes it very hard to disentangle which is which. If you had presented those graphs on a log scale, so you could show, say, fraction of slowdown from one to the other, right? Well, I guess this is a long way of asking, the slowdown between your largest and smallest memory configurations on the two expressed as a percentage of the highest one, what's the difference in the two?
Yes,
right. So if Elasticsearch went 10 times slower in the smallest memory configuration, do you know those numbers?
We can just look at the graph, I think.
I mean, part of the problem is that Elasticsearch with small memory was so slow that tiny differences in the graph, that's why it would be better on a log graph.
I think if you look at the second graph, the right side there, I think the slowdown for the phrase query is sort of the same for the two search engines. And for the single term query, the slowdown, for single term query, I think WiSER is better because reducing memory size has sort of less impact on on the performance.
Right, which is of course the point you're trying to make. So your answer is that it probably didn't actually help very much with the phrase queries. Your better coding helped a lot, but it's got the same memory sensitivity from a higher base.
Let me see.
That may not be true. You should plot this on a log scale.
Yeah.
I know, I wasn't the shepherd for this paper, or I would have made you do that. Thank you.
Thank you.
All right.
Vasily Tarasov, IBM Research. So I might have misunderstood how you performed the evaluation, but Elasticsearch was running just on memory while WiSER was also using?
No, before this figure, all the results are running on small memory and fast SSD.
All right, in both cases. Oh, yeah, all right, thanks. Quick question, the other question that answers, I think, my first question. So you bought the SSD drive, not the SSD, the NVMe drive in the beginning of the presentation. Did you do any cost comparison then between WiSER and Elasticsearch in terms of the hardware resources that you need?
Can you say the question again?
Did you compare the cost difference?
The cost.
Yeah.
We tried. It's pretty hard to comparison, but I think the general rule is SSD is generally an order of magnitude cheaper than the RAM, and another benefit is that RAM costs power, and SSD, if you're not actively using it, it should not cost that much power. But it's pretty hard because SSD fails, and maybe more than RAM. We tried, but we think it's a good first step to go towards that direction.
Oh, thanks.
Okay, so, yep, go ahead.
Ethan Miller, UC Santa Cruz. So the question actually is about the Bloom filters, where you're looking at the Bloom filter both before and after. About how big in kilobytes or megabytes are those Bloom filters?
Good question. If you asking individual ones, I think it's in the paper.
I'm just asking order of magnitude because what
okay.
I'm asking about is, are you reading the whole Bloom filter in, or are you doing the 10 probes individually for each bit you're looking for?
It's discrete. So it's like we may read this portion of Bloom filter and that portion of the Bloom filter.
Okay, so you're reading the portion that has the bit you're looking for.
Yeah.
Okay,
Yeah.
got it.
Okay, one last question.
Hi, I'm Janki from FIU. I was curious about, do you have any idea of how would the search queries look when the searches are very spatially searches have good spatial locality?
You mean have very good locality?
Yes.
Good question. In that case, I think we are targeting the code queries right here. So so in that case, for the code queries, you just read data from SSD and process it. And they can be those hot queries, like in a second, there are multiple same query comes. In that case, my suggestion is to actually use some memory for that and to cache the query results in memory. That way it's easier. But this work is sort of separate, just for the code ones. Yeah.
Thank you.
Thank you.
Okay, let's thank the speaker again.